Good morning all. Today we are going to handle the topic long transmission line. In our previous video sessions we have studied about short transmission lines as well as medium transmission lines. In the case of long transmission lines, the transmission line parameters are considered to be uniformly distributed throughout the whole length of the conductor. You will be able to see that very clearly from this diagram. The long transmission line is divided into n sections, and each section has parameters 1 by nth of those for the whole transmission line. If you consider this section, the resistance of this section is 1 by n of the total resistance of the transmission line. Similarly, with the case of inductive reactance, susceptance and conductance, the analysis of long transmission line is conducted by using the regress method. If you see in this diagram, both resistance and inductive reactance are said to be the series elements. Similarly, leakage susceptance and leakage conductance are said to be the shunt elements. This leakage susceptance is due to the transmission line capacitance, whereas this leakage conductance is due to the leakage current which is occurring at the insulators due to corona effect, etc. Next, we are going to do the analysis of long transmission line by regress method in detail. For analysis purpose, we have considered a small element of length dx at a distance x meters from the receiving end. The indications used are given here. Z is indicating the series impedance of line per unit length. You will be able to see it very clearly. Z is indicating the series impedance. The series impedance is actually formed by resistance and inductive reactance. Since the small element which is considered here is of length dx, the series impedance of this particular element can be given by multiplying Z with dx. As Z is indicating series impedance of line per unit length, therefore for this particular length dx, the impedance will be Z into dx. Similarly, with the case of shunt admittance also, for this element it will be y into dx. This side of the element is said to be end of element towards the receiving end. Similarly, this side of the element is said to be end of element towards the sending end. Hence, we can say that V plus dV is actually the voltage at the end of element towards receiving end. Similarly, V can be said to be the voltage at the end of the element towards receiving end. Similarly, the current I plus dI is said to be the current at the end of element towards sending end, or it can be also said to be the current which is entering into this element, and this current I can be said to be the current which is leaving this element. In order to write the relation for dV, we will consider this shunt element to be placed here. So when this shunt element is being placed here, the current dI will be flowing through this shunt element, and the current which will be flowing through this series impedance branch will be just I. As the voltage at the receiving end is V and the voltage at the sending end is V plus dV, therefore it's very clearly indicates that dV is actually the voltage drop which is appearing across this impedance branch or across this impedance element. As I have just mentioned, whenever we are writing the relation for dV, we have to consider this shunt element to be placed at this particular point. Therefore, the current which will be flowing through this series impedance branch will be I, and the drop which is occurring across this series impedance branch will be IZ dx, and that is same as that of the voltage dV. So the relation for dV can be written as IZ dx. From here we can write dV by dx is equal to I into Z. Next, in order to obtain the relation for dI, we will assume that this shunt element branch is being placed at the right side of the impedance branch. Before, while writing the relation for dV, we have considered this shunt element branch to be placed at left side of the impedance branch, but now we are going to write the relation for dI. While writing the relation for dI, we will consider this branch, that is shunt element branch, to be placed at right side of the series impedance branch. When this shunt element branch is placed here, the voltage which will be appearing across this shunt element branch will be same as that of V. and the current which will be flowing through this shunt element branch will be di. Therefore we can write the relation for di as di is equal to Vy dx, from which we will be able to deduce the relation di by dx is equal to V into y. This can be indicated as equation number 1 and this is represented as equation number 2. In the next step we will differentiate equation number 1 with respect to x. Then the relation becomes d square V by dx square is equal to z into di by dx. For this di by dx we will make the substitution from equation number 2, that is di by dx is equal to V into y. Then the relation gets modified into form d square V by dx square is equal to y z into V. As this is a second order differential equation, and in order to find the solution of the second order differential equation we have to first see the value of y into z. If the value of y into z is greater than 0 means definitely the solution will consist of hyperbolic functions. As you have studied in your previous year's mathematics courses, to determine the solution of the second order differential equation, first you have to write its characteristic equation and then you have to find the solution of the characteristic equation. While solving the characteristic equation, in this case we will be able to get the solution as square root of y into z. Then we have to make that substitution here. So this will be the solution of the differential equation, equation number 3, that is k1 cos h x square root of yz plus k2 sin h x square root of yz. Further differentiating this, we will be able to get the relation like this. From equation number 1 we very well know that dv by dx is equal to I into z. Now you can equate these two terms and from there you will be able to write the relation for current as square root of y by z into k1 sin h of x square root of yz plus k2 cos h x square root of yz. This is mentioned as equation number 5. Now equation 4 gives the relation for voltage and equation 5 gives the relation for current. If you see in these two relations there are actually two unknowns, that is k1 and k2. So our next aim is to determine the values of this k1 and k2. The values of k1 and k2 can be determined by applying the n conditions. The n conditions is at x is equal to 0. At x is equal to 0 means it is actually indicating the receiving end point, because the element which we considered here is at a distance x from the receiving end. So when the value of x is equal to 0 means it is indicating the receiving end point, and when the value of x is equal to L it is indicating the sending end point. L is actually the total length of the transmission line. So by applying this n conditions, that is at x is equal to 0, and making the substitution of V is equal to VR and I is equal to IR, we will be able to write the relation equation 4 as VR is equal to k1 cos h0 plus k2 sin h0. As all of you know that cos of hx is equal to e raised to x plus e raised to minus x by 2, whereas sin of hx is equal to e raised to x minus e raised to minus x by 2. Therefore cos of h0 can be have the value of 1, whereas sin of h0 will have the value of 0. You can make the substitutions in the expansion form which I have told just now, that is cos hx is equal to e raised to x plus e raised to minus x by 2, whereas sin hx is equal to e raised to x minus e raised to minus x by 2. If you make that substitution of x as 0, you will be able to find cos hx is equal to 1, whereas sin hx, that is sin h0 is equal to 0. Therefore, we will get the relation of VR is equal to k1. Next we will apply the same condition in the current relation. The current relation which we have obtained in equation number 5. There, while substituting x is equal to 0 and putting I is equal to IR, we will be able to deduce the relation like this, from which we can obtain the value of k2 as square root of z by y into IR. Now we have determined the values of k1 and k2. Making the substitutions of k1 and k2 in equation number 4 and 5, we will be able to obtain the relations for V and I in this form. From our previous experience, we very well know that our main aim is actually to deduce the value of sending end voltage and sending end current in terms of receiving end voltage and receiving end current. This relation of voltage and current is actually the voltage and current at a distance x from the receiving end. In order to obtain the value of voltage and current at the sending end, you have to make the substitution of x as L that is the total length of the transmission line, just like I have mentioned before. Here the element which is considered to be at a distance x from the receiving end, and the voltage V is actually the voltage at this particular point, and current is the current at this exit point of the element. In effective, we can say that this voltage V and this current I is actually representing the voltage and current relations at a distance x from the receiving end. Therefore, Vs and Is will be the sending end current. In this case, the sending end current is I plus Di. So Vs and Is is actually indicating the sending end voltage and sending end current, and it can be said to be the voltage and current at a distance L. L is actually the total length of the transmission line from the receiving end. So in order to obtain the value of sending end voltage and sending end current, we have to make the substitution of X as L here, where L is actually the total length of the transmission line. So we will be able to obtain the relation for sending end voltage and sending end current as VR cos h L square root of YZ plus square root of Z by Y IR sin h L square root of YZ. Similarly, the relation for sending end current also can be written here. Now this L into square root of YZ can be further simplified as square root of L square YZ. L square can be further split into Ly into LZ. This Y is actually indicating the shunt admittance per meter length. Therefore, L into Y will be giving the total shunt admittance of the line, and L into Z will be giving the total series impedance of the line. The total shunt admittance is indicated by capital Y, and the total series impedance will be indicated by capital Z. Similarly, with the case of the term square root of Z by Y or square root of Y by Z, so we can simply multiply both the numerator and denominator with the term small l, which is actually the total length of the transmission line. So square root of Y by Z will be same as that of square root of capital Y by capital Z. Finally, the relation for sending end voltage and sending end current can be written in terms of receiving end voltage and receiving end current, and the total series impedance of the transmission line and the total shunt admittance of the transmission line. All of you must know these relations, then only you will be able to solve the problems associated with this. In this numerical problem, you are asked to find the sending end voltage and sending end current. The transmission line given is actually a long transmission line. Both the series and shunt parameters are given. The receiving end load details are also mentioned here. So the sending end voltage can be determined by using the standard relation. The value of small y is given in the problem. We can determine the value of capital Y by multiplying it with the total length of the conductor. Similarly, in order to determine the value of capital Z, first we have to identify the value of capital R and capital XL by multiplying the resistance per unit length with the total length and inductive reactance per unit length with the total length. That will be giving you the values of capital R and capital XL, from which we will be able to identify the value of capital Z. In this problem, nowhere it's mentioned about the three-phase connection, so we will assume the connection to be a star one. The receiving end voltage is given as 110 kV. This voltage which is mentioned is actually the line voltage. As we are always doing the analysis in per phase, in order to obtain the value of VR, we have to divide this by root 3. That is very clearly given here. And in order to determine the value of IR, we will use the relation root 3 VL IL cos phi, from which we will be able to find the value of IR as 131 ampere. Now in this relations, we know the values of VR and IR. Next we have to find the value of cos h square root of YZ and sin h square root of YZ. Then only we will be able to determine the value of Vs. From the expansion of hyperbolic functions, we very well know that cos hx is equal to 1 plus x square by 2 factorial plus x raised to 4 by 4 factorial plus x raised to 6 by 6 factorial. Making the same substitution here, instead of x we are having here square root of YZ. So 1 plus x square by 2 factorial plus x raised to 4 by 4 factorial. 4 factorial is actually 24. we will be considering only these three terms, and solving it we will be able to get the value of cos h square root of yz. Similarly, we can determine the value of sin h square root of yz. The expansion for sin hx is x plus x cube by 3 factorial plus x raised to 5 by 5 factorial plus x raised to 7 by 7 factorial. While approximation, we will consider only the first two terms, that is x plus x cube by 3 factorial. 3 factorial is actually 6. So we will be able to obtain the value of sin h square root of yz as 0.1325, angle 74 degrees, 6 minutes. Now we know all the values of VR, IR, cos h square root of yz and sin h square root of zy. Once after determining all these values and making suitable substitutions, we will be able to determine the value of Vs as 67366. This is actually indicating the per phase sending end voltage. In order to determine the line voltage, we have to multiply this per phase sending end voltage by root 3. Similarly, we can determine the value of sending end current by making suitable substitutions in this relation. As I have mentioned before, in the problem there is no specific mention regarding the three-phase connection, so by default we have to consider it as a star connection. The current which we will be obtaining here is actually the per phase current. In the case of a star connection, both the line current as well as phase current are one and the same. Therefore, the sending end current will be same as this value. You don't have to multiply or divide it by root 3. Solving this problem is quite easy, but mainly the students get confused with the relations. So all of you must thoroughly by heart this relation, then only you will be able to solve the problems correctly. With that, we are completing today's session. Thank you.